we're going to try to get to the calculus of polar coordinates via the parametric equations that we've already talked about. So we've already talked about parametric equations, and we can find derivatives and areas under the curve and things like that. And so what we'll do is we'll just use that information. We will relate the polar coordinates with the parametric equations, and then we'll just do the same thing that we did in parametric equations. So let's start off with the idea that x is equal to r cosine theta and y is equal to r sine theta. And then we will use the idea that sometimes we call it r is equal to f of theta, or r is equal to some function of theta. And so what we could do is replace the r with the f of theta. So now we have x as a function of one variable. Now whether we call that theta or t, it doesn't matter. The fact that we're still working with one parameter, t or theta, means it's still going to be a single parameter parametric equation. Yeah? This is still 10.3, yes. So if we're used to parametric equations as functions of t, then we can just replace the function with t. And so we would just take the derivatives the same way we've done before, except the derivative of x is now some form of a product rule, because you have f of t and then you have cosine t. And then the derivative of y is another product rule, f of t and sine t. So it's a derivative of y with respect to t, or with respect to theta. It's going to be the derivative of the first times the second, which is sine, plus the first f, whatever f is, times the derivative of the second, which is cosine. So that's dy dt, or dy d theta. And then you evaluate it at whatever a value is. And the denominator is dx dt, or dx d theta. Evaluated it at a. So we can take one of the examples that we had, maybe the cardioid. Do you remember what the cardioid is with the loop? What's that called? Lima son. So an example would be 1 minus 2 cosine theta. So let's do an example. So this is a limaçon with, that's probably going sideways. So find dy dx. You need to first write the x and y functions as functions of theta or t if you want. Let's use theta. And it'll be 1 minus 2 cosine theta times cosine theta. And the y of t, or y of theta, is 1 minus 2 cosine theta times sine theta. So we need derivatives of these things. dx, d theta. Derivative of the first. Derivative of cosine is positive, negative sine. So minus 2 sine theta. Derivative of 1 is 0. So it's derivative of first times the second plus the first times the derivative of the second So I usually don't care about simplifying, but it might be a good idea to simplify things if you're going to try to put it together and continue to work with it. So I have a negative 2 sine theta cosine theta. I have a 2 cosine theta multiplied by negative. Maybe I should multiply this out first. Minus 2 sine theta cosine theta. And then distribute. That would be a minus 1 times sine theta. And then I have a negative negative is a positive 2 cosine theta sine theta. And I see that I have two terms that are the same except with a negative. So that'll leave me with just sine theta in the denominator. Hope I did that right. So I make a lot of mistakes on purpose. You should try to catch my mistakes whenever they come up. I also make a lot of mistakes by accident. All right, now the y is the derivative of the first. I think it's the same. Wait, the derivative of cosine is negative sine, so this should be a positive, right? You guys didn't catch that? So they don't cancel. So this would be 4 sine theta cosine theta minus 1 sine theta. All right, let's try it again. Derivative of y with respect to theta. So that's the derivative of the first. So derivative of cosine again is negative sine. Negative negative is a positive 2 sine theta. So it's the derivative of the first times the second plus the first times the derivative of the second and now let's multiply everything out. 2 sine squared theta plus cosine theta minus 2 cosine squared theta. Okay. And now I would put them to the ratio. Let's make sure I put the right one up on top. So that's a dy d theta on top and dy d theta in the bottom, or dx theta in the bottom. So I have 2 sine squared theta plus cosine theta minus 2 cosine squared theta. Divide that by 4 sine theta cosine theta minus sine theta. You could use an identity, but it's not going to be that one identity. Sine squared plus cosine squared is equal to 1, but sine squared minus cosine squared, that's equal to like cosine 2 theta or something weird like that. You could try to change everything into cosines or something. But yeah, if this was all they're asking for, then I would be done with this. But then they might ask you some other questions, like what's a tangent line when something. Let's use a theta. So what's a tangent line when theta is equal to pi over 4? So we'll put in pi over 4. So let's do that. Looks like we might need to go to another page. Control X isn't working. Control X, Control C, delete. Now what? What do you do when your Control X doesn't work? I need a new computer. So I guess we also need some information about our equation. No, Control X doesn't work. This is going to take a little longer here. You know what happens with my computer is that sometimes a row, you know, you're typing with your fingers, a finger of keys won't work. No, just a finger. So if X doesn't work, then S probably doesn't work. So for example, I have A, so the A's work, the pinky works. Here is a W, nope, S. So I have to, oh, there it goes, it works now. Let's try, Control X. Control X, ah, yes. All right, good. Just have to hit it once in a while. Okay, so we're making up a problem here. What happens, equation of tangent line at theta is equal to pi over 4. So basically what we want to do is, what do we need for an equation of a line? We need a point and a slope. So we need a point and a slope. So we have the x and y values that would give us our point, and then we have our dy dx that would give us our slope. But remember that to find our slopes and our points, we need to actually put in the values of theta into these things. So let's start with x and y. So putting pi over 4 in here, pi over 4 is root 2 over 2 or something like that. 1 minus 2, root 2 over 2, root 2 over 2, and then whatever that simplifies to. Root 2 minus 2 over 2. Is that right? Did I do that right? Something like that. Anybody feels like giving me an approximation, that would be nice. Meanwhile, I will continue with the y. Oh, this is going to be the same. Pardon me? Great. Negative number. Oh, no. Negative number for x and y just means it's in the what quadrant? Third quadrant? All right. So to find our m, our slope, we need the dy dx. But remember, you don't just flop this whole expression in. You have to evaluate this at the appropriate angle by putting pi over 4 in there. So we have 2 root 2 over 2 squared plus root 2 over 2. That's kind of nice. Everything's root 2 over 2. 4 times root 2 over 2 times root 2 over 2 minus root 2 over 2. All right. So I'll simplify this if anybody wants to give an approximation. You already have it? No. So 4 1/2 2 1/2 plus root 2 over 2 1/2 minus 1. Is it negative 1? Anybody? Maybe? That's what I think I got. I might be wrong. I'm probably wrong.
No, it's root 2 over 2 divided by 2 minus root 2.
Which is not negative 1. So what would this be, approximately? Careful with parentheses in the denominators. Yeah? Positive? All right, we need confirmation.
I got the same.
0.55? That doesn't sound right. Yeah? I don't know. Where? Here? I think that's root 2 over 2 squared. Is it? So it'll be 2 divided by 4. Yeah, it's 1/2. .55? Really? So I'm trying to imagine the the shape of this graph, right? The shape of this graph is a sideways cardioid, or limaçon. And so in the fourth quadrant, or in the third quadrant, because that's where the points are, in the third quadrant. In the third quadrant, I see it as, if it's kind of like a circular shape, imagine a circular shape, then something that's happening in the third quadrant would have a negative slope, wouldn't it? So we might have done something wrong. I say we because we're all in this together. Unless, so we got negative numbers for x and y. So although our pointer is pointing in the first quadrant, it actually gives us a negative number in the third quadrant, right? Well, we put the pi over 4 in for x and for y, and provided I did this correctly, which might be wrong.
But the tangent is positive, the slope is positive. If you see the shape, this is
But that's the second quadrant. I think we're in the third quadrant. All right. What did I do wrong?
Right there, third quadrant, still positive.
Oh.
Right?
Okay.
It's just kind of like a weird
Yeah.
case.
Thank you. That was enlightening. I should have just drew it myself. Because it's not, it's the loop part is happening, well, we'll see. So let's see if I can write down the equation that we have here, which is 1 minus 2 cosine theta. And since I'm using parametric, I went to parametric. I'm going to use t's for this programming. Then I want to go not just 0 to 1. Yeah. Yeah, so there's some points over here where you would have possibilities of positive tangent lines. Thanks. Yeah. Well, that's a small place over here. And when we're at pi over 4, when theta is pi over 4, although we're pointing in the pi over 4 is pointing in the first quadrant, our values look like they were negative, and so they put us in the negative side. So if we draw that point, yeah. So you guys said it was negative 0.293. Negative 0.293. So we're at this point over here.
Yeah.
So that would have that positive slope. And the slope is, we said it was 0.55. So let's do the equation of the line here. So the equation of the line y minus 0.293 negative is equal to 0.55 x minus, and then another negative 0.293. So it looks tangent right there. Whew. So your equation, since that's what the original question was looking for, tangent line, y minus, we can write this whole expression down, or we can just put the estimate. But I think if this was a homework problem, they might be looking for, actually, they might be looking for y equals to something as the equation of the line, right? So you need to actually move this over to the other side. And then the slope. So that's a slope that we got, which translated to 0.55, and then x minus the same thing. So y is equal to negative 0.293 plus 0.55 x plus 0.293. So something like this would be your tangent line. So this should help with somebody asked me a question on Webassign about a problem similar to this. So
I think it might have been me. But I think I hit the ask the teacher that said discuss this with time.
yeah, so this is it.
All right. Thank you.
Something like this, similar to this.
I think the issue with the question was I didn't understand that you were supposed to find the R, then
Well,
plug the
they
equation
didn't.
into R and then take the derivative.
It wasn't like that. The question started off like this. I mean, they didn't tell you that this was polar coordinates. They just started off like this. And so find the equation of the tangent line.
Yeah.
You need to take the derivative carefully and correctly, and then evaluate it at that point. So there's two people that asked me about the same question. So this is how we would work it out. Okay? All right, so derivatives of polar coordinates kind of tie into the derivative of this thing. Let's take a look at the areas now. And area for this is a little bit more interesting because we're not looking at the area between the curve and an xy plane. We're going to look at the area of a sector as this is being drawn out. Now, what does that mean? So I'll just pop the formula up. And then we'll talk a little bit about this. So what we have here is, well, in geometry, you have an area of a sector. So the area of this piece of pie is going to be 1/2 r squared theta. But if you're looking at a polar coordinate graph, and say you're interested in finding the area between angle A, should have used alpha. Let's say you're interested in finding the area within this sector between angle A and angle B. Without going through the whole Riemann Sum story again, what we could do is we can just take a look at a representative slice. So it's clear that we're taking steps by angles. So it's going to be, the angle is going to be d theta. So if we cut this up into an infinite number of theta slices, We could start off with like maybe 4 slices, 5 slices, 7 slices, or whatever. And if we focus on one particular slice, this might be how it would look like. And our slices are being taken by theta, so this little angle over here is actually our d theta. Or, I mean, you can do the triangle first, and then it'll eventually become d theta. The change in theta, that's our angle. So we need the angle and we need the radial distance. Now, the radial distance has 2 radial distances. We have an r here that would represent f of theta sub I, and then another r here that's a little bit different that would represent f of theta sub I plus 1. So you can either do the left-hand endpoint or the right-hand endpoint or the midpoint or any of those other Riemann sum tricks that you could do. The bottom line is this distance over here. What color? Green. Would be f of theta sub I star. And so this one little piece of sector has an area, sector area, just put area. Area sub I will be 1/2. The radial distance is f sub I star, or f of theta sub I star, and then our angle is delta theta. And so we add up a whole bunch of these things, and then you get your Riemann sum that eventually becomes an integral. Yeah? I plus 1. So that just means it's the next angle that you're looking at. Yeah. Yeah. Star just means it could be the left endpoint or the right endpoint or the midpoint or whatever. Any point between theta sub I and theta sub I plus 1. So, and not point, but any angle. Technically, we're looking at angles. Anyways, long story short, this becomes an integral, and that's your formula. For the long story, you go back to Calc 2 and take a look at the Riemann sum business. All right. So that gives us some interesting ideas of things to do. Let's do a cardioid without a loop. That one's going to be a little easier. Let's do an example. So I think one of the other examples that we had was 2 plus or 2 minus or something. 3 plus 2 sine. And it's an upside down heart? Yeah.
The square of the head.
Oh, sorry. Yeah, that should be there. I wrote it so small that you couldn't see it. So. Okay, I forgot it. It's there now. So that's squared. So that's the formula, is the r squared, right? All right, so let's do this as an example, and I think if I remember it correctly, is it upside down? I think it's upside down, right? And I think it doesn't touch the origin. Is that right? I hope so. Now let's take some easy angles, like maybe going from 0 to 2 pi. Not to 2 pi, 0 to pi over 2. Let's find out this area here. Yeah, so it's just the formula. So this is your f of theta. You're going to take f of theta and you're going to square it, and you're going to integrate from a to b. So the area is going to be 1/2 integral from 0 to pi over 2 of 3 plus 2 sine theta squared d theta. And that's it. You're done. Well, you have to integrate it, but I'm done. Zero pi over 2, yeah. So here's our answer. For those people who want answers. So the answer is about 14.639. And if you're going to integrate by hand, you got a sine squared in there. That's usually not very nice. But you know how to do that. Or at least you've done it before. Or at least you've seen it before.
So, got a question like this. That's when you get a nasty problem like that, are you going to expect us to like integrate it by hand, or are you just like, as long as it's set up there, we can calculate it with that calculator, right?
Yeah, so my deal is I usually look for the setting up the integral part.
That's the most important part, the setup of it.
Yeah, and then I may ask you to punch it in your calculator to get a value. Do you guys know how to integrate using your calculator? You integrate using your calculator by putting the function in, and then you would graph it to include the limits, and then one of the things in your calculator says integrate,
Okay.
and then you just integrate.
That's clear.
So in some cases I might want to see the numerical value just so you can check for yourself to see if you got it correctly. You know, if we're finding area and you get a negative number, you know you did something wrong, right? So it's good to quick self-check like that. All right, now the arc length. So here's the formula for arc length. We should try to rederive it again. So maybe I'll take steps to talk about rederiving it, but now I won't finish it. So if you remember at the beginning of class, we changed our r equals to f of theta polar coordinate graph into parametric equations. And then we found derivatives of these parametric equations. F prime theta negative sine theta plus F theta derivative first times the second. I did this wrong.
Yeah. In the first one is not.
Should be cosine, right? Because it's second. So derivative of the first times the second plus the first times the derivative of the second. Now, the formula for the arc length before was to have x prime of t squared plus y prime of t squared. So here's x prime of t and y prime of t, except we're using thetas. So you imagine taking this and squaring it, taking the second one and squaring it. And when you do that, you'll have a bunch of sine squareds and cosine squareds. You also have a bunch of sine times cosine, but the sine times cosine will eventually cancel. And then the bottom line is that your formula will end up looking like this in simplified form. I would encourage you to, if you don't do it yourself, you should at least look at the book to see how they, see how all the sines and cosines and all the trig stuff simplify to this. A video, even better. Yeah.
And in the back of the, in the book, if you go to the practice problems in the back, some of those even have other videos that you can look at. So it's not just the one that you see just in the chapter.
Yeah.
Yeah,
All right, so Webassign, if you pay for it, or since you paid for it, you should take advantage of all the little things that they have. That would include stuff like videos and other things. So let's do the Riemann example again. Or no, let's do a rose this time. I think the rose petal is in your book. Let's do a Riemann. And let's do this in let's do a difficult example. What was it again? 3 minus 2 cosine or something like that? Was it that? I don't know. Yeah, so 2 minus 3. I'm going to change it. Let's pick one. 1 r equals 1 minus 2 sine theta. Yeah, let's do this one. So 1 minus 2 sine theta. And what I'm going to ask for is going to be a little bit tricky. What I'm going to ask for is to find the arc length of this little piece that went into the heart. Sine. So let's see if we can find that little piece that goes into the heart. Now, what is going to be your biggest problem here? We have the f is equal to 1 minus 2 sine theta, and so the f prime is going to be just as easy. What's the So our difficulty for this problem will be trying to find the limits. Okay? You could, but you can just not do parametric and just go from here and set it equal to 0. So over here, we have the Cartesian coordinate, or we have the polar coordinate representation of this, and we know that when r is equal to 0, you're at the origin regardless of what angle you are. Right? So to find out the values where this is going to hit the origin, we should probably set this thing equal to 0. So 0 is equal to 1 minus 2 sine theta. And I think this particular problem, we get nice angles. Some of the problems that you get, you won't have nice angles, so you'll have to do some extra math. I think this is a 1/2 when you bring the 1 over and then divide by -2. So when is theta equal to 1/2? So theta is equal to 1/2 in a bunch of different angles. And there's an infinite number more.
Is this between 0 and 2 pi only?
Yeah, but if we're dealing with this graph is between 0 and 2 pi. So if we're just going between 0 and 2 pi, then these two would be the two graphs that we would be interested in. If this was sideways, it would have been a little bit trickier, and you probably would have been looking for some angles between -pi/2 and +pi/2, which would make you think a little bit more. The other way to do this is to graph the Cartesian coordinate version of r and theta. And if you remember the graph, I think we started here, we went up, and we went down, and then we went back up. So these two places, no, that's not right. I think it goes down first. 1, 2. So it goes down. So these two places over here are the two angles that we would be looking for. So it's always good to try to relate the Cartesian graph with the polar graph and then try to see where the aspects are. That's kind of like why we did that exercise on the board. As we go around the angles, you'll figure out where to go. All right, so our arc length from here, it should be, oh, I still need to take the derivative. So the derivative of r with respect to theta is -2 cosine. And that's it. So those are the things that you would put into the formula. So your arc length is going to be equal to the integral from pi/6 to 5pi/6. And the square root of the derivative is a -2. The negative will go away. Cosine theta squared plus the original function. So in terms of an exam situation, I would say set up the integral to find the arc length. You'd be good here. In terms of finding an approximation using your calculator, should we do this one using the calculator? All right. Whatever. So I would want to draw this nasty looking integral.
Wait a minute.
What happened? Was there a question? Did we get that resolved? Okay, I want to go to function, mode, function. And then I want to pretend that my thetas are actually x's. So I have two functions here, so let me get rid of the other one. All right, I have a big square root. This is going to be long. I'm going to ignore the negative because if I square it, it'll become positive anyways. So that's just 2 cosine x. And I want to close the cosine parentheses and square it. Plus, open parentheses, 1 minus 2 sine x. Close that parentheses and square that. And then close the square root parentheses. And then I want to integrate from pi over 6 to 5 pi over 6. 5 pi over 6 is, I don't know what it is, but it's less than 3, right? 3.14. It's less than pi. Is it? Yeah, it's still less than pi. So I'm just going to graph this. I'm going to adjust my, maybe I'll have it zoom fit first. Where's the fit? Was it 0? And then you may need to adjust the window. Yeah, totally. I don't even know what the limits are here. So I'm going to go back to the window. And I want to go from my x from 0 to somewhere like 3. And then my y values, see, that's the tricky part, is I don't know how high this is going to be. So I'm going to go with maybe, I can assume that this is positive, so maybe I'll make this at 0. I'll make it a little bit negative. Negative 1. And then I'll start off with 3 and adjust it if I have to later. X res. The delta x is the number of steps you take. And let's just graph it for now. All right, so now let's integrate. Let's go to, I think it's under, yeah. If you're getting dimension error, then go to second function and y equals, and then press 4, because you have some statistics plots there that are bothering you. So I want to go to, sure, I want to go to second and trace, or it's actually doing some calculations. And number 7 is an integral of f of x. So I'm going to hit number 7. It's going to ask for the lower limit. I want my lower limit to be pi over 6, so I'm going to hit pi divided by 6. Enter. It's going to ask for the upper limit. The upper limit is going to be 5 pi over 6. Enter. And then I don't really care about the picture because that's not doing anything for me. These all came from polar coordinates, and this is some weird function in polar coordinates. But the value of 2.68 whatever is the value that I would be interested in. Whoa, what happened? So, remember what we did? You got y equals this whole thing. Graph with an appropriate window. That would include your limits. And that would go from something a little bit less than 0 to something that would be able to capture the top. Actually, capturing the top is not that important. And then you go to second function and trace, which is really calc. And then you look for the integral of f of x symbol. You input your lower limit and then your upper limit. And then you hit enter. Okay, so this is your TI 83, 84 calculating integrals. So you should practice this in case on the test I ask you to find a nasty integral. And then, you know, I would ask you mainly to set up the integral, and then I would ask you to use your calculator to estimate it to like 3 decimal places or something. Yeah. Oh, yeah. If you have an 89, then you can find the antiderivative for most of these symbolically, which is kind of nice. 84, you need to graph it. Yeah, with 89, there's a special integral formula or integral symbol. All right. Hey, we got 3 more minutes. You guys, we done?
I was going to ask you what you did for the window, because it's not coming out.
Yeah, I got nothing.
I guess we're done.
Did you get nothing?
I got something, but it's
Yeah.
window dimensions.
All right, we're done. These guys are over here in front.
Up at the STEM Center.
All right.
This week's just got kind of weird hours for the first week.